We've finished up on the traditional probabilities and the approach to or I should say, the sample space approach to calculating probabilities. And we said that there were some ideas in there that we liked and that we were going to carry forward into statistics. And we're not quite back there yet. Again, it was just a brief discussion on some basic ideas, and then now we want to talk about probability distributions, and then we'll see how those tie in to what we do in statistics. And so we're going to start out, and again, this book may or may not be the book that you have, but the concepts, again, these are all the same things. And but here we see probability distributions, and they start out with a definition. They say random variable. And think of a function in algebra. A function has numbers that you would input into it, and then something happens to those numbers. There's some operations performed on those, and then you get some output. And a random variable is just a function whose outputs are probabilities. So we see it says a random variable that has a single numeric value. So remember that a function has only, that pairing that you talk about when you define a function. So, so each input has one unique output, and it says that it's determined by chance for each outcome. So we have a number that comes from a sample space. So we think of our inputs coming from a sample space going into the function, and then the associated probabilities of those sample space values are the outputs of that probability function. So, and then it says a probability distribution is a description that gives the probability for each value of that function. It's often expressed as a format or a table, a formula, or a graph. And this is really just an algebraic idea. And if you think back in algebra, you dealt with like linear functions. And sometimes you had a quadratic function, and you had a polynomial, a higher degree polynomial function, and so on, exponential. And there were lots that you looked at, and you would see a graph of the results or what the outputs looked like um, given all the inputs. And so the same idea is that we kind of have these graphs that we look at, and these outputs, we talked about like linear functions and quadratic functions and so on. And you have different shapes of probability distributions also, and they have their own special shape depending on your sample spaces and the how they're defined. And so this is nothing really new in general. It's just the terminology is kind of new, and we do have to remember we're working with inputs and outputs that are producing probability. So let's go over to the next page, and we see a discrete random variable and a continuous random variable. So discrete random variable has finite or countable number of values, okay? And one of the problems with discrete random variables is that the numbers get very large. When we worked with factorials, we found out that the sample spaces got very large very quickly. So it didn't seem to want to work very well if we were going to define a distribution of data by a discrete random variable. That we were going to run into problems very quickly. And as data grew larger, the computers got better, and we were able to evaluate larger and larger sets of data with lots and lots of variables. And then the computers just couldn't handle the sizes of the sample spaces. So we really we talk about discrete random variables, but we really use continuous random variables to do our probability approximations. Continuous random variable is one that has infinitely many values, so infinite number of possible or not countable situation, and so we'll talk more again as we look at the examples, and we're going to um, look at an example using a table first, and I'm going to skip over. So let's say that we have a situation where we're looking at job interview mistakes. Okay? And so that occurs all the time. People have job interviews. You'll have probably a job or had job interviews, and you might have made some mistakes. And some are more common than others. And the first thing I want you to notice, now that we've left the probability chapter and looked at kind of some very basic ideas, is that when we were like flipping a coin or rolling a die, we were always saying that, each value was equally likely to occur. So if a die had 6 numbers on it, each number had a 1 out of 6 chance of occurring. And that doesn't really happen very often in reality when we collect data. Like this example, in fact, if we list the top job interview mistakes, we have 1, 2, 3, 4. The top 4, let's say: inappropriate attire, being late, lack of eye contact, checking phone or texting. So, and we look at that and we say, you know, something's not right here. But they're saying that inappropriate attire happens 50% of the time. Being late happens 44% of the time. Lack of eye contact happens 33. So these are definitely not all equally likely to occur according to this table here. Okay. Now, if we have a table and we have some probabilities, one of the things that we always like to find with discrete random variables or the mean and standard deviation, just like when we had a set of data values. And you'll see some formulas here. The sum of the x times the p of x is, right? Here's the sum of this is the deviations about the mean. The score is the squared deviations about the mean times their probability of occurrence. And this is kind of like a weighted mean is really what it is. And for the deviations. And so we see all this, but we're going to, look at the calculator to do these computations. So let's go ahead and talk about another term they use for the mean, and the expected value. Okay, so the expected value of a discrete random variable is the mean value of the outcomes. Okay, E equal mu. E can also be found by evaluating x times p of x, right? Where we just had that formula. Okay, and I'm going to not do this by hand again. I want to show you how to do these in the on the calculator. And I think what I'm going to do, I'm trying to find. And this is 195. I got to get to the right page here. Okay, there we go. Okay, so I want to use this table right here. And again, number of girls in 4 births. So we could talk about a distribution and then a sample space. And here on the left side, here's our sample space. The number of girls in 4 births could be none. You could have no girls, or 1 girl, or 2, or 3, or 4. So these are all the possibilities. Remember, the sample space lists all the possible things that could occur. And again, our example is, okay, we want to see in 4 births how many girls we're going to end up with. And the chance of not getting any girls is 0.063. Right? Chance of getting 1 girl out of those 4 births, right? 0.25, and 2 girls, 0.375, 3, and so on. Okay. Now we would say that this is a discrete random variable because we have a countable number of inputs, so it's discrete. And we also, over here, these numbers are all numbers between 0 and 1. So a little review there. Probabilities are between 0 and 1, so that this all checks out. And if we add these numbers up here, then we will get basically 1, okay? So this, again, it was probably a little rounding, it's just a tiny bit off, but if we sum up the probabilities in a discrete random variable, they will equal the probabilities that we want to 1. Now, the next thing I want to do is use a calculator. Okay. So we need to go into hit stat, and I'm going to move this over. I'll bring it back in a second. Okay. All right. So stat. I'm on edit, and I'm gonna hit enter right there. Okay. I need to get rid of these data values. I'm going to highlight L1, hit clear, enter, and I've got these cleared. Now, to find the mean and standard deviation in a discrete random variable, I need to put the inputs over here in L1, and those were 0, 1, 2, 3, and 4. All right, those are the numbers that I got from that table right there. That was the input. 0, 1, 2, 3, and 4. And then on the right of that, I'm going to type these probabilities in L2. Point 0.063, enter, and 0.250, 0.375, 0.250, and it looks like that distribution is symmetric, so 0.063, enter. Okay, so I got the data in. Again, if you just put it in basically the way the table is all set up. All right, so we have, there we go. So again, these numbers are over here. So I'm gonna again pull this out, so we don't need this right now. Okay, so to get you do the same as you did before when we were finding mean and standard deviation. Remember, we had to go to stat, calc, 1var, enter. Here's the only difference right here. The frequency list, you have L1. L1 is the number, and then we got to put L2 here for the frequency list. So second function, the number 2 key, L2 right there. and then go to calculate. So really pretty easy. There's our numbers. The mean is 2. Standard deviation, look, it's nothing. There's nothing there. So does that mean there's a mistake? Well, yes and no. There is a mistake in this calculator here, but it's not there. That should be blank. And this is the number. Right here is your population standard deviation. We're working with a theoretical distribution about the population. So that's what this is showing. Here's my standard deviation of the population, 1.00, and so on. Okay, so we got the mean and standard deviation. So that's pretty straightforward. The rest of this stuff we don't need. Just the mean. That should be mu. That's where the mistake is. It should be mu equal to 2, not x bar. Mu equal to sigma, right, equal 1. These little x's really don't mean anything down here. Okay, so pretty easy for the mean and standard deviation. All right, we're going to go on to another formula, and that is on okay. Let's go ahead and clear this out, and then we're going to go over to page 'll pull this back over here. Okay. All right. Now, the formula that I talked about, it works in general for discrete distributions. Now, in this section, we have to remember that there are lots of different distributions. Just like in algebra, you have linear functions. That wasn't the only type of function. It was one of many. And it's the same with discrete distributions. There's lots of discrete distributions, and this one happens to be the most popular one, the binomial, and it's kind of the most flexible one. The binomial distribution is what we refer to as a discrete random variable, and it's by far the most popular. It's the easiest to understand. It's kind of like the histogram. Remember, the histogram could be used at any level of measurement. It was easy to understand. And same with the binomial probability, the discrete. So it's still around. And one of the reasons why is that the binomial, you can take any situation and make it binomial. You could think about letter grades. You could say, well, how does the state look at achievement? And do they look at A's and B's and C's and D's and F's or something like that? And actually, not necessarily. They're usually concerned with, what's your percentage of successes and failures? And what that means is if you pass, your success, A, B, or C, doesn't matter. It's just the idea is, did you pass or not? Did you get A, B, C, or did you not get an A, B, C? Because there's lots of other things. You could get D or F. You could get a withdraw, an incomplete, a no-show, they suspended. So there's lots of things that fall in a non-success. But that's a binomial situation because there's only two things that are recognized: success or failure. That's it. So we've already talked about some binomial things, like flipping a coin is binomial, right? Heads or tails. Every single trial, only one of two things could occur. And we just talked about the births. We showed that example of the births and how many girls in 4 births. But that's a binomial situation because on any given birth, it's either going to be a boy or a girl. And there's lots of things that you can look at on and off and true and false, right? We talked about true false questions, things like that. And so uh, it's very popular. And so it's a good discrete distribution to talk about. But again, remember, it's only one of many. And what we want to do is just kind of take a quick look at it. Now, there is a formula that goes with the binomial. And that's really what I want to look at here first. These are just kind of what we talked about, fixed number of trials, independent, like flipping a coin, the heads and tails. We talked about how those are independent trials. Sample space doesn't change. Outcomes have to fall into one of two categories, success and failure, and so on. So, and you can all this notation, there's lots of stuff there. But let's kind of get to the formula. And it's not quite as bad as it looks. Okay. All right, here we go. Using the binomial. And this is the formula right here. This P of X equal to n factorial. So that should look familiar. This n factorial over n minus x factorial, x factorial. This right here, this part of this formula is the formula for combinations of n choose x. This is the independent multiplication rule here for P and Q, or the success, probability of success and probability of failure. How many successes, how many failures. So these are independent, this is dependent. This is one of those problems I talked about where you have a dependent component and an independent component all kind of wrapped up together here. Now, before you get too concerned about this formula, right, it's actually very easy on your calculator. So let's go ahead and look at an example, and we're going to use the calculator. So it says, given that there's a 0.85 probability that a randomly selected adult knows what Twitter is. So we're either saying they do know what Twitter is or they don't. That's it, right? All right, so that's all we got to know, 85%. So let's go down here. It says that given that n is 5, so we're going to ask 5 people, right? 5 adults, randomly selected. What's the odds that 3 of them will recognize Twitter, right? So I'm going to move this over again. And you're going to go to second function, distribution, right here above the vars key, right? And you see right here, we're going to go down. Lots of distributions in there. Okay, binomial PDF. That's the one that we want. That's that formula we just looked at. So we put in how many trials? We said there was 5. Probability given was 0.85. So that's the probability of success on any given single trial. 85% chance of someone, person, adult recognizing Twitter, what Twitter is. X is the other number, the 3. That means that's the probability we're finding. The probability of 3 adults out of 5 recognizing Twitter. We hit paste. There's our binomial PDF formula, which some of you on the other calculators, sometimes this is all that comes up right here. Binomial PDF. And you type this in. Enter. And there's our percentage. And you'll notice that the book here, they they did it, this 0.138, right? They used the factorial keys and stuff and did all that, factorials, and multiplied this, and right, same thing. It's the exact same thing, right? What we did there. So, all right, so let's do another one. And what he's showing here, this is using technology. StatDisk, again, that's the free software that comes with the MyMathLab. But they're just showing here, you can get like the table, the whole table, rather than just the binomial distribution. And we don't really need that, but this is, if you want that, it's definitely available. You can get all the values all at once. But on the test, I'm going to ask you to do like one thing. And let's go ahead and move forward on that. Now, every discrete distribution has its own formulas. You have the one general set of formulas for mean and standard deviation. But the book here is showing, this is on right here, the mean for the binomial distribution is mu equal 1 times p, and the standard deviation square root of n times p times q. All right, so let's go ahead, and we're going to go back and use that information we had for the last problem. Okay, we're going to find the mean and standard deviation for that distribution. So again, the mean was equal to n times p. So the mean was equal to 5, because there were 5, right? Remember, said 5 adults we were going to ask. P, the probability of somebody recognizing Twitter as an adult, was 0.85. And all right, so that, right, remember we did 5, 0.85, and then 3. So we just take 5 times 0.85 and get 4.25, right? So there's our mean. Of 4.25. Right, standard deviation, remember I'm using this sigma, so that's the population standard deviation. This is the population mean, mu, square root n times p times q, which is equal to square root, n was 5, p 0.85. Careful with the parentheses. I think you gotta be careful when you use them. And q, so q is 0.15. Okay. So how did I get that? So Q is the complement of P. Q is equal to 1 minus P. In this case, Q is equal to 1 minus 0.85, 0.15. Okay. So complement is what's left over. So P is what we were looking for. In this case, that's a success, and Q then was everything else, which is a failure. There's only two things, right? Whatever P is and whatever Q is. In this case, a girl or a boy. So this, again, we will get our calculator. Square root 5 times 0.85 times 0.15. Enter. So again, this is our population, standard deviation, 0.798. All right, so we're going to round it there. Okay, so mean and standard deviation of a binomial, right? This works for the binomial, and then if you were using like a geometric or hypergeometric, some other types of Poisson discrete distributions, they'd have their own formulas. And we're just going to look at the binomial, and that's it. And now the one thing that I want to finish up with, another problem here, and we'll go through all this, and I need to add, we skipped the complement back. Uh, let me clear this. Let me clear this. There we go. Okay. Now, I said I'd come back to it, and I want to do another problem. And let's say that we have want to solve a probability problem, ones that they call at least, or we want to know of some value or more, some value or less, because coming up with a single value is nice. There's nothing wrong with those probabilities, but that's not really what we normally look at. And what I want to give you an example of is this. Let's say that we were going to buy a carton of eggs. So we have 1 dozen of eggs and equal to 12. And you know, when you go to the store and you look at eggs, you open a carton because you want to see if any of the eggs are broke. And if there's one broken in there, then you won't buy that. You'll like open up another, maybe take another carton. Um, but that's not wouldn't help us understand our problem if we wanted to say what's the probability of a broken egg. Let's say okay, P equal 10%. Okay, this P equal 10%. And would we be able to answer uh, maybe a real question by saying, okay, what's the probability of having them all, or one getting one broken egg? But in reality, if there were 2 broken eggs, you wouldn't buy it either. You wouldn't buy the carton of eggs if there was 2, or if there was 3, or 4, or 5, or 6, always up to 10, right? So really, that's what I mean by an at least problem. So the reality of it is we would really need to find, okay, what's the probability of 1 or more broken eggs, right? That's what we really would like to know. If we were manufacturers and we were shipping them and they were getting into the stores, I mean, our goal would be that there would be no broken eggs, but we know that there's always going to be something, go wrong somewhere, and there'll be 1 or 2 or 3, and normally when you open them up, there isn't like a bunch of them. It's more likely that it's 1 or 2 or something, but we need to figure in all those probabilities. So 1 or more. Now that's a pretty tall problem because what does or mean? That's the addition rule. So if you remember, I talked about the addition rule before because we have lots of problems that deal with the idea of the addition rule, where we say 1 or more a lot, or 2 or more, or 3 or more, or 5 or less, or 8 or less, or whatever. When we say or, we'd have to add, like in this case, to find out the answer to this, we would have to take the probability of 1 plus the probability. Remember, it's the addition rule. And we would say, okay, these are mutually exclusive events. You can't have one broken egg and two broken eggs at the same time, right? It's either one or it's two or it's three or so on up to probability of 10 plus probability of 11 plus probability of 12, right? So we'd have to do all of those. Well, there's a lot of times when we can use the complement. So what's the complement to this problem right here? The complement okay. Now, in this case here, the how many broken eggs could there be in a carton? Well, 0 or 1 or 2 or 3 or 4 or 5 or 10 or 11 or 12, right? Always up. Now, this problem, I'm taking 1 into 12. We got to put those all together. So I got to take all these, right? We'll call that A. That's A. Probabilities of all from 1 to 12. The complement of an event is what's left over from what you're looking for. So if I'm looking, okay, that's A. This then right here becomes not A, or the complement of A. 0. Okay, well, how does that help us? Well, the probability of A plus the probability of not A, or its complement, say not A, is equal to 1. All probabilities in a given experiment, remember we said they have to add up to 1, so here's a little algebra here. The probability of A, I'm going to solve and move this over to the other side of the equation. 1 minus the probability of not A. Okay. So if I look at this formula here, this is hard to find because I got to do all of these. This is easy to find because I just have to take 1 minus, there's only one number here, so that's going to be pretty easy to do. All right, let me, all right, let's see what I got. All right, so we're not going to do this. All right, so now probability of 0 equal to, how do we find that? Well, we use the binomial formula, right? That's binomial. PDF. We have 12 eggs, 10% chance of any one of one broken on any given single trial, right? So any given single egg being broken, 10% chance. And we want to know 0. What's the odds of 0 broken out of 12, given that each egg has a 10% chance of being broken? Because what we're trying to do is this over here. So this is going to be equal to 1 minus the probability of 0, which is equal to 1 minus. Okay, so I need to plug that into the calculator. Now let's clear this out. Second distribution, binomial PDF, trials 12 eggs, 10% chance of any one being broken. We want to know 0. Paste. So you'll see there's our, all right, what we got here. Plugged it in, and we hit enter, and we get 0.28, right? 2824. We're just going to say 0.28. It's close enough. So we're going to go back over here. 1 minus 0.28 equal to the ends. We're just going to subtract this. Is going to be 0.72. Okay. So that is what? That is our probability, right, of A. Because we did the complement, which was 0.28, subtracted it from 1 and got its the original one we were looking for, right? So pretty easy if you use the complement. It's a good deal in probability theory. For us, again, we're just kind of looking at this stuff pretty quick, even with the discrete distributions, because we're not going to use this formula much as we move forward. We still have something else to talk about in the next chapter, but that's the next unit. So this is going to be it for this particular unit, and then we're going to move on in the next video. Okay.